heartfelt and warm welcome to my video, my dear respected audience. Good morning, my name is Obijit Chakraborty and I am currently pursuing my Bachelor of Technology degree in Electronics and Communication Engineering at Kuch Bihar Government Engineering College, and I am currently in my 5th semester. Today in this video, I will try to explain the different types of single sideband modulation techniques, which include DSB-SC, DSB-LC and VSB. The explanation is part of my CA1 internal assessment for this semester, so I hope you will like and value this effort and explanation. So to start with, we have an introduction to what is single sideband modulation. So a single sideband modulation usually works in radio communication and is a type of modulation used to transmit information such as an audio signal by radio waves. It is a refinement of amplitude modulation and it uses transmitted power and bandwidth more efficiently. Amplitude modulation produces an output signal, the bandwidth of which is twice the maximum frequency of the original baseband signal. Single sideband modulation avoids this bandwidth increase and the power wasted on a carrier at the cost of increased device complexity and more difficult tuning under receiver. Radio transmitters work by mixing a radio frequency RF signal of a specific frequency, the carrier wave, with the audio signal to be broadcasted. In AM transmitters, this mixing usually takes place in the final RF amplifier, high-level modulation. It is less common and much less efficient to do the mixing at low power and then amplify it in a linear amplifier. Either method produces a set of frequencies with a strong signal at the carrier frequency and with weaker signals at frequencies extending above and below the carrier frequency by the maximum frequency of the input signal. Thus, the resulting signal has a spectrum whose bandwidth is twice the maximum frequency of the original input audio signal. And we further come to much introduction to SSB, such as this is an example of the spectrum of AM and SSB signals. The lower sideband LSB spectrum is inverted compared to the baseband. As an example, a 2 kHz audio baseband signal is modulated onto a 5 MHz carrier to produce a frequency of 5.002 MHz if upper sideband is used, or 4.998 MHz if lower sideband is used. Now we come to the DSB-SC or double sideband suppressed carrier transmission in the single sideband transmission. So double sideband suppressed carrier transmission is a transmission in which frequencies produced by amplitude modulation are symmetrically spaced above and below the carrier frequency, and the carrier level is reduced to the lowest practical level, ideally being completely suppressed. In the DSB-SC modulation, unlike in amplitude modulation, the wave carrier is not transmitted. Thus, much of the power is distributed between the sidebands, which implies an increase of the cover in DSB-SC compared to amplitude modulation for the same power use. DSB-SC transmission is a special case of double sideband reduced carrier transmission. It is used for radio data spectrum. This model is frequently used in amateur radio voice communications, especially on high frequency bands. So if we come to the spectrum part of the double sideband suppressed carrier transmission, it is basically an amplitude modulation wave without the carrier, therefore reducing power waste, giving it a 50% efficiency. This is an increase compared to normal AM transmission that has a maximum efficiency of 33.333%, since 2/3 of the power is in the carrier, which conveys no useful information, and both sidebands containing identical copies of the same information. Single sideband suppressed carrier is 100% efficient. This is a spectrum plot of a DSB-SC signal. Now if we come to how a DSB-SC signal is generated using a mixture. The signal produced is the product of the message signal and a carrier signal. The mathematical representation of this process is shown below, where the product to some trigonometric identity is used. Now here we have the message signal, which is used as an input to a mixer along with the carrier signal, and we have an output of a modulated signal, which is shown here by modulated output. Now we come to the demodulation of DSB-SC. For DSB-SC, coherent demodulation is done by multiplying the DSB-SC signal with the carrier signal with the same phase as in the modulation process, just like the modulation process. A resultant signal is then passed through a low-pass filter to produce a scaled version of the original message signal. The equation above shows that by multiplying the modulated signal by the carrier signal, the result is a scaled version of the original message signal plus a second term. Since omega c is much greater than omega m, this second term is much higher in frequency than the original message. Once this signal passes through a low-pass filter, the higher frequency component is removed, leaving just the original message. How DSB-SC works. This is best shown graphically. Below is a message signal that one may wish to modulate onto a carrier consisting of a couple of sinusoidal components at frequencies respectively 800 Hz and 1200 Hz. The equation for the message signal is S of t half cos 2 pi 800t minus half cos 2 pi 1200t. The carrier in the signal is a plain 5 kHz CFT equals to cos 2 pi 5000t sinusoid as pictured below. The modulation is performed by multiplication in the time domain, which yields a 5 kHz carrier signal whose amplitude varies in the same manner as the message signal. X of t equals to cos 2 pi 5000t, which is the carrier signal, which is mixed with a half cos 2 pi 800t minus half cos 2 pi 1200t, which is the message signal. And here is the graph showing the output message. The message is indicated by the green curve and output is indicated by the blue curve. So the name suppressed carrier comes about because the carrier signal component is suppressed. It does not appear in the output signal. This is apparent when the spectrum of the output signal is viewed. In the picture shown below, we see 4 peaks. The 2 peaks below 5000 Hz are the lower sideband LSB and the 2 peaks above 5000 Hz are the upper sideband USB. But there is no peak at the 5000 Hz mark, which is the frequency of the suppressed carrier. So now we come to another important part of SSB, which is DSB-LC or double sideband large carrier. For broadcast system, many RX for each TX, it is more economical to obtain less expensive receivers. For such a case, a larger signal is transmitted with the AM DSB-LC to eliminate the need of local oscillator in RX. The AM DSB-LC signal is given by theta AM f of t cos omega ct plus AC cos omega ct. And here we have a graphical explanation which is shown below. In it, it states phi of AM t is to pi f omega plus omega c plus pi f omega minus omega c plus pi AC delta omega minus omega c plus pi AC delta omega minus omega c. Now we first see the generation of the DSB-LC signal. It is much similar to the DSB-SC signal, just that when the message signal of k cos omega ct is divided in 2 parts and mixed with 2 times with the carrier signal of f of t and give an output of phi AMT. And it is generated using 2 methods which are shown below. The first method is the switching chopper modulator rectifier modulator. It is shown as in the circuit below. Now we come with the generation of DSB-LC signal using non-linear devices, which is generally used. In the previous figure, the diode is not operated as an ideal switch. The nonlinearities in diode characteristics may be given as I of t is to A1 E of t plus A2 E square of t plus A3 E cube of t plus it goes on till infinity. Therefore, from the figure, V AB of t, A1R f of t plus k cos omega ct plus A2R f of t plus k cos omega ct whole square equals to A1 capital R k cos omega c t plus 2a2 r k f of t cos omega c t, which is the amplitude modulated signal, plus other terms which is suppressed by bandpass filter, which gives the final result as V output of t a1 rk cos omega ct plus 2a2 rk f of t cos omega ct. Now we come to the part of demodulation of AM DSB-LC signal. It is done using two methods, using synchronous coherent detection, the same as in DSB-SC, that is direct connection and pilot carrier, which is the high cost method, and it's done also by asynchronous detection, which is generally used method. Non-coherent detection, it is also called envelope detection since it is extracts the message from its envelope. It is low cost and applicable only when m is less than equal to 1. So at first we come to envelope detector. It is a very simple, efficient and cheap demodulator. For correct detection, the charge time should be fast and discharge time RC should be slow. In PHSC is charged, while in NHSC is discharged through R. Usually this circuit is followed by low pass filter to eliminate unwanted harmonic content. Now we come to the most important part of the SSB, which is the vestigial sideband or VSB. Limitation of single sideband modulation being used for voice signals and not available for video TV signals leads to the usage of vestigial sideband. The vestigial sideband in radio communication is a sideband that has been only partly cut off or suppressed. Television broadcasts in analog video formats use this method if the video is transmitted in AM. Due to the large bandwidth used, it may also be used for digital transmission such as ATSC standardized 8 VSB. The broadcast or transport channel for TV in countries that use NTSC or ATSC has a bandwidth of 6 MHz. To conserve bandwidth, SSB would be desirable, but a video signal has significant low frequency content, average brightness, and has regular synchronizing pulses. The engineering compromise is vestigial sideband transmission. In vestigial sideband, the full upper sideband of bandwidth W2 equals to 4.0 MHz is transmitted, but only W1 0.75 MHz of the lower sideband is transmitted along with the carrier. The carrier frequency is 1.25 MHz above the lower edge of the 6 MHz wide channel. This effectively makes the system amplitude modulated at low modulation frequencies and SSB at high modulation frequencies. The absence of the lower sideband components at high frequencies must be compensated for, and this is done in the IF amplifier. This is an example of figure showing vestigial sideband modulation. Signals such as TV video, facsimile and high-speed data signal have a very large bandwidth and significant low frequency content. SSB may be used to convert bandwidth, but practical SSB modulation systems have poor low frequency response. DSB, on the other hand, works well for messages for significant low frequency content, but transmission is twice that of SSB. Vestigial sideband modulation offers the best compromise between bandwidth conservation, improved low frequency response, and improved power efficiencies. In the vestigial sideband modulation, most of one sideband and a vestige or a trace of the other sideband is transmitted. The typical bandwidth required to transmit a VSB wave is about 1.25 times that of SSB. The VSB modulated signal is produced by passing the DSB-SC or normal AM signal through a filter known as a VSB filter, which removes a part of one of the sidebands. Here is a figure showing a typical TF of the VSB filter as shown. An important and essential requirement of each VSB of F is it must have a relative response of half of FC. It must have odd symmetry about FC. The transition level is 2 beta hertz. Value of the VSB signal is FM plus beta hertz, that beta is less than FM. To derive a time domain expression for the VSB signal, H of VSB F is H of SSB F minus H of beta of F, where H of beta of F is the difference between the response of the SSB and VSB filter. Now, assuming input to the VSB filter to be a DSB-SC signal, we have the following VSB modulator and VSB synchronous detector. Here we further calculate it to get V in of f equals to f DSB of t equals to AC f of t cos omega ct. F of VSB of t equals to half AC f of t cos omega ct minus half AC f of t sin omega ct minus half AC f beta of t sin omega ct, which is the SSB, VSB and VSB part combined, where half AC f beta t sin omega ct equals to response of h of beta of f to the input AC f of t cos omega ct. F VSB of t equals to half AC f of t cos omega ct minus half AC gamma of t sin omega ct, where gamma of t equals to f cap of t plus f beta of t. If gamma t equals to 0, then f VSB t tends to f SSB t. If gamma t equals to f cap t, then f VSB t tends to f SSB t. The transmitted power is bounded by 1/4 of AC square f of t square bar less than p VSB less than half is square f of t whole square bar, which is also stated by f p SSB less than p VSB less than p DSB. And now the spectrum of the message of the vestigial sideband to be modulated is shown as the following graphs, which are A, B, H, VSB of F, C, D and E respectively. This is also an example of a two-side spectrum of a VSB. And now we come to envelope demodulation of VSB signals. It is often desirable to combine the envelope demodulation of amplitude modulation with bandwidth conservation of VSB signals. Adding a carrier to a VSB signal is given by f VSB of t plus carrier equals to AC f of t cos omega ct minus AC gamma t sin omega c plus AC cos omega ct. For normal amplitude modulation, gamma of t equals to 0. For SSB carrier, gamma of t equals to f cap t. For VSB plus carrier, gamma t takes an intermediate value. The envelope of f VSB of t plus carrier is f VSB of t equals to r of t cos of omega ct plus phi t plus carrier, where r of t equals to envelope equals to AC of 1 plus f of t root over 1 plus gamma square of t by 1 plus f of t whole square. It can be seen that RT is distorted if gamma of t is much less than 1. The distortion is negligible and R of t is approximately equal to AC of 1 plus f of t. As in the normal case for VSB with carrier, average transmitted power is P of gamma is approximately equivalent to P of C plus BC f of t whole square under bar. Commercial TV broadcast use VSB plus carrier with 30% vestigial sideband. Example, TV video signal, which is a bandwidth of 4.5 MHz for normal AM transmission, and bandwidth of the amplitude modulation as 9 MHz for VSB transmission, and of the VSB as 6 MHz, thus saving 1/3 of the bandwidth. Now we can conclude the topic by describing what is amplitude modulation. In electronics, telecommunication and mechanics, modulation means varying some aspect of a continuous wave carrier signal with an information bearing modulation waveform, such as an audio signal which represents sound or a video signal which represents images. In this sense, the carrier wave, which has a much higher frequency than the message signal, carries the information. At the receiving station, the message signal is extracted from the modulated carrier by demodulation. In general form, the modulation process of a sinusoidal carrier wave may be described by the following equation: m of t equals to a of t into cos omega t plus theta t. A of t represents the time varying amplitude of the sinusoidal carrier wave, and the cosine term is the carrier at its angular frequency omega, and the instantaneous phase deviation phi t. This description directly provides the two major groups of modulation: amplitude modulation and angle modulation. In angle modulation, the term A of t is constant and the second term of the equation has a functional relationship to the modulating message signal. Angle modulation provides two methods of modulation: frequency modulation and phase modulation. In amplitude modulation, the angle term is held constant and the first term a of t of the equation has a functional relationship with a modulating message signal. The modulating message signal may be analog in nature or it may be a digital signal, in which case the technique is generally called amplitude shift keying. For example, in AM radio communication, a continuous wave radio frequency signal has its amplitude modulated by an audio waveform before transmission. The message signal determines the envelope of the transmitted waveform. In the frequency domain, amplitude modulation produces a signal with power concentrated at the carrier frequency and two adjacent sidebands. Each sideband is equal in bandwidth to that of the modulating signal and is a mirror image to the other. Standard amplitude modulation is sometimes called double sideband amplitude modulation (DSB-AM). The disadvantage of all amplitude modulation techniques, not only standard AM, is that the receiver amplifies and detects noise and electromagnetic interference in equal proportion to the signal. Increasing the received signal to noise ratio, say by a factor of 10 or 10 decibel improvement, thus would require increasing the transmitted power by a factor of 10. This is in contrast to frequency modulation in digital radio, where the effect of such noise following demodulation is strongly reduced so long as the received signal is well above the threshold for reception. For this reason, AM broadcast is not favored for music and high fidelity broadcasting, but rather for voice communications and broadcast, sports, news, talk radio, etc. AM is also inefficient in power usage. At least 2/3 of the power is concentrated in the carrier signal. A carrier signal contains none of the ordinary information being transmitted, voice, video, data, etc. However, its presence provides a simple means of demodulation using envelope detection, providing a frequency and phase reference to extract the modulation from the sidebands. In some modulation systems based on AM, a lower transmitted power is required through partial or total elimination of the carrier component. However, receivers for these signals are more complex because they must provide a precise carrier frequency reference signal, usually as shifted to the intermediate frequency of a greatly reduced pilot carrier and reduced carrier transmission of DSB-RC used in the demodulation process. Even with the carrier totally eliminated in double sideband suppressed carrier transmission, carrier degeneration is possible using a Postas phase lock loop. This does not work for single sideband suppressed carrier transmission, leading to the characteristic Donald Duck sound. Such receivers may slightly detune. Single sideband amplitude modulation is nevertheless used widely in amateur video and other voice communication because it has power and bandwidth efficiency, cutting the RF bandwidth in half compared to standard amplitude modulation. On the other hand, in medium wave and short wave broadcasting, standard AM with a full carrier allows for reception using inexpensive receivers. The broadcaster absorbs the extra power cost to greatly increase potential audience. So these are the websites I referred to through my project, where I obtained the written information from Wikipedia and I helped myself by explaining from YouTube. I got all the images from the last 4 websites, which are the Electronics Coach, Electronics Post, Java Point and Google. So thank you for listening to my explanation for my report and I hope you guys like my video. Thank you.